Now, to those of you who've done Riemann sums, which of course you should have done some Riemann sums while you're doing integrals of functions of one variable, you remember how painful the process is and slow. So you can imagine it'd be much more difficult to do Riemann sums with double integrals. Thankfully, we won't have to do that. Okay, we're going to do a trick using iterated integral technique to get the volume under the graph without having to partition our region and summing up the volumes of the rectangular prisms. Nonetheless, it's important to define formally at least the double integral as you see above. We're dealing with rectangular regions, so we're going to describe these rectangular regions as x being between a and b and y being between c and d. Looks just like a rectangle. And so how do we do this iterated integral approach? Well, take your function, okay, which you want to do a double integral for the region described this way, and fix x, okay? Just set it equal to some x naught. Here we're pretending x naught is just a constant, okay? So fix x to x naught. And now your function of two variables is, in quotes, a single variable function, okay? You're only thinking about y as varying if x is fixed. And so you're only concerned with what will you plug for y, right? X is already some values plugged in, and we're done with that one. So we're looking basically at a slice of this function along along the trace at x equals x naught. Okay, and now integrate the function from y equals c to y equals d. Okay. What is that going to give you? Well, if fixing x naught gave you a slice, you're going to get the area under the of that slice, right? So you'll get the area under the curve. Which curve? The curve of this quote function of one variable, where x naught is fixed at a value and y is allowed to vary. So this then will give you the area of that slice. Okay. Now, what's the volume of a area of the slice? Well, it's not a volume, right? The area is area, and it's two-dimensional, and the volume is three-dimensional. So let's take then that area and give it a width. We're going to give it a very small width dx. Okay, we're going to give it a very small width dx, and so we'll get a slice that's now a little fatter with width dx. And now this is a volume. Okay, so ax naught dx is a volume of area ax naught and width dx. And this is all formal, so it's just to motivate the understanding. We're doing this formally. And what do you want to do next? You want to add up all the slices, the volume of slices that you would get as you vary x this time. So x was fixed before. Now let's not fix x anymore, and let's vary it from a to b, and we're going to add up all the volumes ax dx as we vary x from a to b. And what we should then get is a volume. Okay, so here we're going to do the double integral this way. We're going to say that it's the integral from a to b over dx of the area of each of these slices, which when multiplied with dx gives you a volume. So you're adding up all these small volumes. And what is ax? Ax was the integral from c to d. So you have then this value. This computation should give you the volume under the graph. So if we integrate first over dy, holding x fixed, and literally just treat x as a constant as you're integrating over dy. And so integrate y from cd, where x is just treated like a constant. Then integrate the variable x from a to b after you're done with the inside integral. And the net result should be the volume under the graph. So you might have wondered, well, why did you fix x first? Why didn't you fix y first and carry out this computation? That's true. You can do that. And in fact, when we're dealing with rectangular regions, it's really easy to switch the order of integration. So we have here the theorem by Fubini. If the function f is continuous on a rectangular region, given here, then the double integral of f over r may be evaluated in either order. So you could have integrated c to d over dy as we've done above, and then done the integral over dx, or with impunity you could switch them, right? There's no problem with switching them. Just switch them around. So switch these two symbols around and switch these two symbols around, and you get that expression that you see there on the left, and you will get the same answer either way. Now, pause for 1 second and listen carefully, right? You cannot do this, switch with impunity, just switching the symbols, when we deal with more general regions, only for rectangular regions. That doesn't mean you can't switch the order of integration when we deal with more general regions. We will switch the order of integration, but it's not as simple as merely moving around these symbols, okay? When you have rectangular regions, in other words, C, A, B, D, all of those are actual numbers, then you can just switch the order of integration very easily. You know, you could switch them as you would symbolically. When we deal with more general regions, which we might have functions as our bounds, you got to be careful, and we'll discuss this topic in the future. So let's take a look at an example. So in this example, we want to find the volume of the solid bounded by this surface, given here, okay? And over the region R, which you could view as on the XY plane, okay? And this is a rectangular region. You see it because of the bounds of just numbers being used here. And we're going to use both possible orders of integration. So this surface stays above the region R, so it stays above the XY plane, the region R, because it's strictly positive over R. So we have no complications of the function dipping below the region R and having a negative value. So all we have to do is compute the double integral to get that volume. Now, that's not to say that you can't get a negative volume. You can. We got negative areas when dealing with integrals of functions of one variable. We could similarly get zero or negative volumes when graphs of functions dip below the XY plane. But we want here we want the volume bounded by this surface and the region, so we don't want that complication occurring, and it won't because the function is strictly positive over R. So let's do this by integrating over x first. Okay, so here is x, and we're going to integrate x from where to where? From -1 to 1. That's what's described by region. So from -1 to 1. And then we'll integrate over y from what? From 0 to 2. Okay? And how do we carry out this integral over x? Well, we treat y as a constant. Okay? So y is treated purely as a constant there. So what is the integral of 4? Well, it's 4x when you're integrating over x. What's the integral of 9y squared, x squared when you're integrating over x? Well, treat y as a constant. And so the only thing that gets quote integrated is the x, and so you'll get 3 x cubed, okay, because 9x squared is the integral of 9x squared is 3x cubed, and so that's where that's coming from, and y just comes along as a constant there. And evaluate the integral from -1 to 1. How do you plug these values in? Where do you plug them in here? You plug them into x, okay? So you'll plug 1 into x, you'll plug 1 into x cubed, okay? You'll get something, and then you subtract that same expression, but with -1 plugged into x, and you should get 8 plus xy squared. there if you do that. And then integrate over y, and this is now just a integral with one variable, so we get 32. Now what if we wanted to integrate over y first? So now what do we do when we integrate over y first? We treat x like a constant. So we get 4y, 3x squared, y cubed. Okay? And now plug in your bound. So plug in the bounds. Where do you plug in the bounds now? You plug them into y. Okay? So 2 goes into here, and then you subtract from this expression with 2 plugged in, the same expression but with 0 plugged in. Okay? And you will get 8 plus 24x squared. Okay? That 8 is coming from 4 times 2, and the 24 is coming from 3 times 2 to the third, which is 8, and so you'll get 24, and that x squared is just coming along for the ride as a constant. Okay, treat x as a constant while you're integrating over y. And now we just do the integral. This next integral is just the integral of one variable, and so you get 32. So what are the key lessons here practically for computing these? When you integrate over one variable, treat the other as constant, and when you plug in the bounds, plug them into the variable that you just finished integrating over, right? So here we just finished integrating over y, so we plug our bounds into y, not x, okay? And what allows us to treat the variable as a constant, again, that's the idea of finding the area of a slice first, and then computing the second integral to get the volume. So here's how the function looks that we just integrated. We wanted to find the volume above that greenish region there, but below the orange surface. And if we do the integral over x first, we hold y constant, and what you see there is the slice where y is held constant, okay? And so that slice, how do you get the area of that slice? You do integral over x. We could then, of course, vary the y, and we get these different slices, and so we'll take each of these areas, multiply them by dy to make each of these slices a little fatter, right? So it becomes a volume with width dy, and add up all of these small volumes to get the total volume. Okay, that's the idea of the iterated integral. And what if we chose to integrate over y first instead of x? So if we integrate over y first, we're holding x fixed, and so we get a slice along x that you see there, a slice where x is fixed. And if we vary that, we could take the area of area of one of these slices, multiply it by dx to make it a volume, and then add up the volumes of all these small slices to get the total volume. Either way, we get the same answer, which was 32. And that also, I'd like to remind you that when you integrate over one of the variables, you hold the other one fixed. So as we're integrating here, we're integrating the variable y first. X is fixed, and that's why you're getting the area of a slice there, because x really is fixed at that value. Okay?